Good morning, everyone. It's our pleasure today to listen to Professor Andrew Bunger, who's going to give this online ARMA Hydraulic Fraction Technical Community Seminar on October 16th, 2025. Andrew Bunger is a professor in the University of Pittsburgh's Department of Civil and Environmental Engineering, and he joined the university um, in 2013 after spending approximately 10 years in Melbourne, Australia working in CSIRO. Prior to that, he received his PhD from geological engineering from University of Minnesota. And his interests include the mechanics of hydraulic fractures, characterization of stresses within the earth, time-dependent failure of materials, ranging from rock to human bone, and application of large language models in engineering and beyond. For those who don't know, Andy served as a president of the American Rock Mechanics Association from 2023 to 2025. Okay, Andy, the floor is yours.
All right, thank you so much, Yegor and John McLennan, for the invitation. Thank you for being open-minded to something a little different. John approached me a month or so ago, and I said, well, what I've been thinking a lot about and working on lately is a little off axis for the typical talk, but hopefully it'll be interesting. And I find that, it's whenever you kind of take an opportunity to go into another field, you end up learning more about your own field as well, because you start looking at where the commonalities lie and it gets you thinking in a different way. I've certainly found that. And so I think this journey from rock to bone and from hydraulic fracturing to neurosurgery has definitely taught me a lot, and something that I'm appreciative of the opportunity to share a bit today. So I got into it, really, the story has to do with time dependent breakage of materials. And that's kind of the underlying subtext or underlying mechanism that draws this commonality. The way I got into this was a number of years ago. Um, we had a few projects. One of the ones that kind of stands out was something we did along with Roman Priul and that group at Schlumberger Dole Research. Um, we were really interested in this kind of conundrum. So when you're trying to initiate multiple hydraulic fractures, and if I sketch out a schematic of two locations where you might have perforation. So this would be like two of multiple um, possible initiation locations along a single stage. Um, and I've drawn schematically a longer notch to indicate where the rock might be weaker or there might be a lower stress. It's a kind of cartoon representation of the fractures easier to initiate here, harder to initiate here. So here's the conundrum. The pressure comes up, and eventually the weakest point or the lowest stress point or whatever starts to grow. Now, what we know when we look at timings, and we know all the more now because of distributed sensing, that typically our pressure either falls off a bit or maybe levels off. It might especially level off if we're using, a limited entry approach. And so how do we ever get this fracture to initiate? I mean, either the pressure's got to keep going up by quite a bit after the first one initiates, which is a lot to expect. Um, and I mean, theoretically, and this is something I see Ali is on the line. You can look theoretically, you probably expect a couple hundred psi of potential increased pressure after the first initiation. But that's not a lot compared to the variability, say, in stresses you can get along a stage. Um, so the other possibility is that this one initiates later, and we need a new mechanism by which it can, or to understand the mechanism by which it initiates. Because if we consider just your classical breakdown criterion or a K1 equals Kc type of criterion, the issue here is that when the pressure has leveled off, this one is only ever going to see pressures that it's already seen and it didn't initiate. So we need some kind of mechanism by which it can initiate at a subcritical pressure. That's the premise. So that at later time, additional locations can initiate. And I think there's a growing body of evidence from distributed sensing that indeed it is the case that we can get multiple fractures growing within a stage for sure, and that they don't all initiate precisely at the same time. There is some kind of time dependence to the initiation. So we studied this a few years ago. We were interested in predicting whether that delay time would be less than or greater than the pumping time, and whether there were strategies by which we could reduce it, because reducing that delay time could lead to a more uniform distribution of fluid and proppant within a stage, and eventually, hopefully, more uniform and effective production. We looked at this in the lab with some tests that look like a typical block test. We isolate a section of the block and we pressurize it, but instead of ramping up at a, say, constant injection rate like we normally would do, we actually hold a constant pressure and we measure the time until the fracture initiates. So we sit at a constant pressure, measure the time, and sometime later the hydraulic fracture initiates. And we got some results that look something like this. So here's for granite. We did this in granite. We did it in sandstone. We did it in limestone. We actually saw the phenomenon, but never published it in shale as well. The problem with the shale is that it's so variable that it's really hard to get a systematic variation in the lab. So you can see delay, but it's very hard to do anything that sort of shows anything systematic because you're so beholden to the variability from one sample to the next in shale. With the granite, the sandstone, and the limestone, we could get very uniform samples. And so we could get results that look like this. Here's an example. We pressured up to 16 MPa in the wellbore. We got initiation of a hydraulic fracture within a few seconds. Exact same scenario, another sample, minute and a half at 14 MPa. Go to 12 MPa, it took like almost 10,000 seconds. So, an hour and a half or something like that. And, very systematic relationship. As we increase viscosity, we increase the delay time. We get same phenomenon in sandstone. We get some dependence upon pressure. I'm not showing it here. We did the same thing in limestone, and we showed in limestone you can get some dependence on the chemistry of the fluids. So we were using water versus hydrochloric acid, and we can see that there's some similar behavior and that this delay time increases. There's some fluid component, but what we also believed is that there's some kind of rock component here as well. So it's this interplay between fluid and rock, a really nice fluid-rock interaction problem. So that took us the next step down the path, which is to get the fluid out of the system and just look at time-dependent breakage of rocks. And so what we did was we ran some three-point beam tests. These are on, I'm going to show beams of granite here. And we ran them again, a little bit different than what we would normally run a three-point bending test. Normally you would ramp up this load P until the beam breaks. And you have a formula by which you can calculate the maximum stress generated in the bottom at the center of the sample, and you would use that as some measure of the strength of the material. But instead of doing that, we are going to hold at a load that is insufficient to break the rock right away and measure the acoustic emission until the time of failure. And so you see something like this. This is a test that ran for about 6 hours, so 20,000 seconds. Over those 6 hours, you can see the cumulative events. So this is fixed load for about 6 hours. Cumulative events kind of bump up quickly at first, then kind of level off, and then slowly accelerate, and then rapidly accelerate. If we look in the details here at position, so this is the X position, so X being the location along the sample of the events relative to the eventual observed fracture plane, you can see we get a burst of events all through that portion of the block that gets that initial stress. And then there's this kind of depletion. The rate drops right off. Until eventually you get this acceleration. This acceleration involves a coalescing of the events around the eventual fracture plane. I think we're really seeing, all the suitably favorably oriented sites kind of pop right away, but they deplete. And then we enter a regime where one microcrack begets another. This is the process of microcrack coalescence. So if we look at the event rate, it actually has an interesting pattern. You can see, so this is just the derivative of the cumulative events curve. You can see that the event rate falls off over kind of the first 40% of the life of this sample. So like 2.5 hours. And then the remaining like 3.5, 4 hours of its life, it's slowly accelerating with a final burst at the end. So what's interesting here is if we look at a multitude of tests, so here's 6 tests, and step back from it. Don't look at the time scale just yet. Just look at the shape. You can see they all have the same shape with a decreasing event rate for the first like 40% of their lives, roughly maybe 50% or 20% in some, closer to 50% in others, but kind of half or a little less than half of the life, decreasing event rate, slow acceleration, rapid acceleration. Now, if we zoom in, we can see this plays out over a whole range of time scales. So this is less than a minute. This is like a few minutes. This one is 5 hours. This is 6 hours. This one's about 8 hours. And this one is, let's see, this one's a couple of days at over 150,000 seconds. This is about 2 days long. And the same shape takes place regardless of how long the test took. And we were varying the loading, the loads, making them smaller in order to get a longer delay time. Okay, so that was interesting. And more recently, I revisited this. I was inspired by there's a really excellent keynote, the Heimson lecture given by Qinghua Lei at the last rock mechanics meeting. I got inspired to go back to this data by looking at some work that he's been doing in landslide prediction, rock pillar bursting predictions that uses this theory that was brought up in the 80s, really firstly spawned by predicting the eruptions of Mount St. Helens in the early 80s. Voigt wrote a paper in 1988 and then a follow-up in 89 that presents this rate-dependent material failure law that says that when a material is becoming critical, there's some measurable, so omega is some measurable quantity, classically strain or displacement. There's been some work with AE energy. We're probably not a lot, but some we're going to use AE energy. So the acceleration of that measurable is proportional to a power of its rate. Voigt presents this as kind of I think the word that he uses is really interesting and unknown. Why? But if we integrate it, you can see that we have this very striking divergence of the rate of this measurable as we approach a critical time, TC. That's the failure time. So as time is going to TC, as long as this exponent alpha is greater than 1, we get xc greater than 1, so this exponent's negative, and this thing blows up to infinity. So it diverges, the rate diverges to infinity as time goes to TC, as long as alpha is greater than 1. So this is the definition of this positive feedback that leads to unbounded growth and hence a catastrophic failure. Voigt actually finds that alpha is around 2 for a lot of materials. It is the value that gives dimensional consistency. If we get time at the end, I might show another thought on why alpha might be close to 2. So what we wanted to do was have a look at, can we detect the onset of criticality in our AE data? So if we rearrange this, we're not the first ones to do this. This is something people have done over the years in the literature. Just divide both sides by the rate and plot this ratio of acceleration to rate versus the rate in log-log coordinates, and a linear relationship with a positive slope indicates the terminal stages of failure, to use Voigt's terminology. Okay, so that's what we want to do. In our experiments, we need to define our measurable. I'm going to do that as the cumulative AE energy. And I'm going to very roughly approximate the AE energy as the product of the amplitude defined here as my peak amplitude times the duration, which is how long the signal stays above my detection threshold, So AE energy is probably somehow proportional to that. I'm not worried about whether I'm precise with it. I'm more interested in getting something that is scaling with the total energy produced. Um, so then I'm also, in order to get the units to not be really kind of hard to read, I'm going to normalize this by the median event energy so that what we're basically seeing when we see omega is it's going to be like median event equivalent energetically. So when we see it as a rate, it'll be kind of energetic event equivalent per time. Okay, so now we can look at our 6-hour test. This is now just using single sensor um, and looking at this period of time after the event rate starts to increase and highlighting that here in the blue dots. So this is that period of time. I'm going to highlight it here. And you can see that when we plot the ratio of acceleration to rate over rate, it's very much linear. Indicate and very much positive slope, indicating that there's according to in Voigt's terminology, the positive feedback is kicked in and the material is progressing to failure, and alpha is pretty close to 2. Okay. So this criticality exponent 2 is also going to be consistent, we're going to see in a minute, with a linear decrease of the event intra-event period. And that's going to end up being really helpful to us. So this, again, is kind of a classical way of predicting time to failure. I'm going to use the inverse velocity approach, where we're going to take this rate-dependent material loss, solve it for the inverse velocity. And if alpha is pretty close to 2, this inverse velocity is going to go to 0 roughly linearly as the rate diverges. And so when that happens, we can move a window across our data, project it out to anticipate TC, and that will give us an estimate of the time to failure. Okay, so how this looks here, when we take this section, I'm going to highlight it in blue over here, and it's these dots here. And what we can see is that it does go linearly to 0 with a couple different slopes. There's some slope changes. Something that Dr. Lay and his collaborators have looked at is in things like landslide predictions, where you don't want to have false positives like evacuating everybody here too early. There's some higher order methods you can use to deal with these kind of changes in slope. I'm not going to do any of that here. We're just going to see, all right, we can get just simple linear projection. All right, we're in the right order of magnitude of time to failure. It's 17,000 seconds rather than 22, and then it refines as we get closer to failure time. And if we look then at the time to failure that we predict from that and plot it versus time, we get the black dashes here, or the black line here. The red is the actual time to failure because we know when the sample failed. And you can see our prediction is actually really good over the last like 30% of its life. Here's that part where it was under predicting the time to failure, but it gets better and it's a pretty useful prediction. Would have been nice when we were running these tests, we could have planned out a little bit better so that we knew if we had real-time monitoring about when the tests were going to fail. But this inverse velocity method, kind of a classical method in natural hazard forecasting, seems to work really well for this really basic delayed fracture of rock beams. Going across all 6 of the tests, we see they all establish critical state in the lead up to failure. That's in these blue lines. It's not as obvious in the really fast one. We were missing a lot of events because they were coming really fast they were right on top of each other. So, it wasn't a detection rate issue with the equipment, is that literally the events were on top of each other within the same window that you record in order to record an event. But these that have longer duration, you can really clearly see the establishment of critical state. And we have linear, or sometimes with a couple of slope changes, progression to failure in every case. And in every case, we are able, for about the last 30% of the life of the specimen, even over the last 8 hours of the life of this specimen that lived for a couple of days, we can very clearly see that the failure is coming, and we can predict it really very well using this inverse velocity approach. Something that I found really interesting with these, and I can't really explain very well yet, but I'll present it as a observation that intrigued me, is that it's not fully monotonic, this progression to failure in every case. Some of them progress fairly monotonically, but others have these like mini cascades. So if you look here, there's a little mini cascade, and if you project it out, it's actually not a terrible order of magnitude estimate of the time to failure. You can see it here on the time to failure plot right there. If you look at the actual time to failure, it's not bad. And if you look at these other mini cascades, you can see they're all giving us decent estimates early on, long range forecasts of how far we are, order of magnitude from failure. It seems to know that somehow this test is going to last tens of thousands of seconds, and another test is going to last hundreds of thousands of seconds, even early on, by the way that the cascade proceeds, which I find very interesting. I don't know why in some cases the cascades are terminated and in others they just march away to failure. It'd be really nice to understand and something we'd like to look at more in the future. Okay, so now enter the neurosurgical application. So I've been working on this area and thinking about it for quite some time. When I got a call, I've been asked, and Yegor even asked me at the beginning, like, how did you sort of end up down this path? I got a call, a reach out from my colleague, Dr. Mike McDowell, who's now at Penn State. He was at Pitt at the time a couple of years ago when we started working on this. He's a pediatric neurosurgeon. And he reached out because he had this problem and he thought maybe somebody who looked at geophysical signals or something like this who's used to predicting when rocks or tectonic plates or something would fail, maybe they could help with this problem he was experiencing as a pediatric neurosurgeon. So here's the application, then I'll get to the problem. So for those who are undergoing clamped neurosurgeries, which is anything that is cranial based, meaning that there's access going through the cranium or up through the nose, anything that's accessing the brain, that's about 1 million surgeries per year. The way that patient's head is held still so that the surgical team can work safely on the patient's head is with a clamp that looks like this. This is a Mayfield. There's another brand called Adoro. And it's a 3-point fixation. So on the one end is a screw that's turned by hand. It's actually got a calibrated spring inside so that the surgeon can turn this screw. There's a little indicator that sticks up out of the middle of the screw, and they can see, are they applying 10, 20, 30, 40, 50, 60 pounds of force to the single pin side. There's a double pin side on a rocker mechanism here. And these pins are designed to poke through the skin and lodge in the skull. That's actually much better from the perspective of both having solid fixation because you're into solid tissue rather than soft tissue. And also, if you try to do this, sometimes people ask, why don't you just use soft pads? You're clamping pretty hard to hold the skull still. It would be very hard on your skin and soft tissue. You would come out with quite a lot of soft tissue injury from that. It's actually much better to poke through the soft tissue and lodge in the skull. Now, here's the design problem for them. They need to clamp with a large enough force to avoid slippage, but not so large so as to induce skull fracture. So there's the window. And typically, that window is comfortably at 60 to 80 pounds of clamping force applied to the single pin side. Of course, that's roughly divided into on the 2-pin side. That window is typically fairly comfortable for adults. At 80 pounds. You typically don't induce skull fracture in a healthy adult. However, for a pediatric patient, that window can be very narrow, almost non-existent for some pediatric patients if they have a very thin, immature skull. It's very difficult to clamp hard enough so that the skull doesn't slide without causing fracture. Here's a patient from summer of 2024. It's treated here at UPMC in Pittsburgh. This is a pediatric patient, and you can see here in their postoperative CT scan that the pin actually punctured straight through the skull. That was actually detected during surgery. Remedial action was required. It was disruptive to the procedure, but the patient was able to recover. But this is the sort of thing that is very disruptive and can be very dangerous for the patient and can lead to complications. We actually did some looking at procedures that are used in pediatric neurosurgery. There's about 300 pediatric neurosurgeons in the US. About 64 of them responded to us. And what's really striking here is that among those neurosurgeons, there's such a wide range of practice. There's actually no standard of how to clamp a patient of a given age. So youngest age to clamp without other support. So there's other types of devices that can help support the skull and avoid the fracture all over the place. You can see this curve. Most say about 2, but there's a wide range of practices. Age considered safe to pin as if they were an adult. Wide range of disparity. Some say they have to be teenagers. Some will clamp as if an adult at 4 years old. Maximum pressure, they all kind of agree around the adult pressure, which is 60 pounds, but minimum to avoid slippage all over the place. Some will clamp with very low loads. So they kind of make it up based on the age of the patient. We'll have a very young patient. Maybe I'm going to only clamp with 15 pounds of load. Is that enough? Totally depends on who you ask. So wide range with no evidence of consensus. So here's how often these surgeons, very underreported in the formal reporting databases. But if you look at surgeons who are reporting skull fractures, over half say that they get skull fractures from time to time, and 30% or so experience one or more fractures in their patients per year. We didn't control on the caseload for these surgeons, so it's possible that if we normalize by caseload, we could get a much clearer picture of how often it happens per case. Scalp lacerations, so that is when the pinning is insufficient and the pinning becomes unseated and slips. So slippages are fairly common. More than 70% experience at least one slippage per year. Those slippages can sometimes cause laceration. This is the most common patient injury in neurosurgery, is the laceration of the scalp because, and this is very common in adults as well, because the pinning was insufficient. So, and 70% believe that there's insufficient safeguards. So what we wanted to do was to provide a means by which a surgeon can tell, is this patient progressing to fracture, or even did I just cause a fracture? We'll see that at the end. So that the surgeon can clamp sufficiently to avoid laceration. We also want to detect if slippage is setting in, which would be the clamp loosening over time due to creep of the skull. And by doing that, provide an early warning that the surgeon could intervene in either case to avoid fracture or slippage. So here's where we took this then. We went into the cadaver lab and we started looking at AE associated skull breakage and also slippage under pinning loads. So we installed an acoustic emission detector. In the first case I'll show you is just breakage, which is at the single pin side where the load is largest. So this is a modified pin with an acoustic emission transducer attached. I'll show you also a slippage case where we put modified pins at all 3 locations. Slippage tends to happen at the double pin side because of the lower normal stress at the double pin side. So we're using human cadaver skulls. In the case of fracture, we are thinning the skull with a surgical drill to simulate immaturity. So a mature adult skull of a healthy adult is able to withstand hundreds of pounds. We've actually gone to 500 pounds of load before we've fractured an adult skull with a pin. So in order to simulate something more like an immature skull on a pediatric patient, and thankfully, in the absence of pediatric cadavers, we thinned the skull using a surgical drill so that it had a thickness that was more like an immature skull. I did this in multiple locations, mostly on the frontal or temporal bone of formalin fixed skulls, and then applying stepwise and increasing force, detecting the AE with our system. We believe the skull will exhibit some behaviors we've seen in rock that include that we could get both immediate and we could get delayed breakage of the skull. That for time delayed breakage, we would have AE signatures that increase in rate and magnitude in the lead up to breakage, that there would be a cascade that would allow prediction of time to failure, that after breakage, we would have an aftershock sequence. I'll show you that at the very end. And I won't spend much time on this, but we also get power law distribution of the AE magnitudes, which we see in both the rocks and I won't show it here, but we do see it in the AE magnitudes from the skull. Okay, so here's an example of one of our tests. I'm going to show firstly a video that kind of shows the progression. These events are going to look really small because I scaled it, the amplitude here. You can see the little buzz. So a lot of them are small. I put them all on the same scale so you can see more easily the rising of the amplitude as we approach failure. This point here is where the pin actually punctures through the skull. You'll see the event rate increasing, and you'll see every dot is going to be a new event. You'll see the trace of the waveform of that event down here. This is a video we took. I'm going to have you watch this side first, and then I'll play it again, and we can watch what happens in the video. So if we hit here, so you can see now the events are coming, fairly small amplitudes. And now in the lead up, you'll see more events. There's this kind of escalation. And lots of events, much higher amplitudes, and there the skull breaks. So now, if we watch this again, now watch this side. So this looks like a hole, but it's actually where the skull has been thinned. So skull is actually about 1 centimeter thick here. We've thinned it down to about 1 millimeter. So under the pin is about 1 millimeter of intact skull. Dr. McDowell's kind of searching for an angle he can see better here. But now watch in about 3, 2, 1, now. And there. So I hope you saw it go through. You can see the pin actually punch straight into through the skull. That punctures through and was essentially the same mode of failure as we saw in that CT scan of the pediatric patient. So the event amplitude and the event rate both escalate in this time leading up to failure. But what we're interested in is through this period, we had some sense that maybe we were generating events, but that there was a kind of stability with a kind of decline of event rate. But it's kind of hard to see looking at it this way. We had some sense that we had a destabilization happening here. And the question is, can we discern where there's stability so we would not throw a false alarm? And can we see earlier than the last few seconds where the material starts progressing to failure? So if we look simply at the inverse AE energy rate, so this is an inverse rate method, we can actually see that exactly this approach is very useful. So remember, when we see an increase in the inverse rate, that's indicative of alpha less than 1 in our original rate-dependent material formula, and hence stability. So this is indicative of stable behavior. This is something that would tell us that we are not progressing towards a catastrophic failure. But as soon as we go from 30 pounds to 40 pounds of load, you can see, even though the escalation of the rate was not apparent until much later, looking at it previously, we can see it right away, that this starts to cascade to failure, and we're able to start getting predictions of time to failure. And if we look at this time to failure prediction, we can see over the last roughly 30 seconds, we have a really good prediction of time to failure. And we would have thrown a warning probably 40 seconds or so. Once we saw this establishing failure cascade and that it did not, blip back up like it did here, we would have thrown a warning that would have stopped the procedure and would have allowed intervention. So probably would have given about 40 seconds to act, which in this case, in a surgical setting, is sufficient. I'm told by Dr. McDowell all that would need to be done is support the head so that the patient's head is supported by the surgeon's skull, reach under the drapes, and if it's a fracture, loosen the clamp. If it's a slippage, which we'll see in a minute, support the skull, reposition, and repin. Okay, so we have a few cases that we could show, but I won't for the sake of time, that kind of repeat the same idea with delayed fracture. I want to also look at slippage. So slippage is much more common. There's actually a lot of forces that are applied to the skull by the surgical team during the procedure. And also the skull is undergoing creep. And so with it being fixed here, with this pin on a spring, you can actually have the patient coming unpinned or getting a lower pinning load during the course of a surgery, which these are often hours long, almost all, they're 10-hour procedures, sometimes anywhere from hours to a full day procedure. So can we detect when slippage is setting in? So what we did is we built a frame. It's rough, and you'll see the load diagram is not, quite what we wanted. We have a better idea we're going to go back to the cadaver lab with, but this is a screw drive. We had full cadavers here, so we had to have something we could take to the cadaver lab and sort of position around an entire cadaver. But the idea is to pin with sensors at every sensor, and then to provide an escalating load to the forehead and push out of the clamps and see if we can detect when slippage is imminent. So we actually implemented a real-time monitoring for all three pins. So this is single pin side. These are the two pins on the double pin side. I've blocked out the face of the patient, and the camera's kind of turned on its side here. You can see this load that is pushing the head out of the clamp. And we're going to join partway through, and it's a little hard to see because the rescaling of our real-time method is not great on the screen. But the point I want to make is we're getting most of our events, about 85% of them, at pin 3. So this would tell us immediately the slippage is happening at 3, not at 1 or 2. You can see the events are starting to come more regularly, and you'll see this turn red and then purple. That is where our warning system, there it is, based on the Cascade, is kicking in and telling us that the pin has most likely failed. The pinning has come unseated and it's starting to slip. So we wanted to prove the concept. Could we stop before there was patient injury? And in this case, there was no laceration on the patient's scalp. And so we decided to stop as if this were a surgical procedure and see if there actually is slippage, and if so, did we detect it? So here's what we detected. Here's the failure cascade versus time. There were actually 2 failure cascades. That's what threw that warning, that there was a progression to failure. This is actually not a cascade. It has an undefined slope. This was actually what happens with some instrumentation. So there was some touching of the sample, and there was a burst that did not cascade. It has an infinite slope here. It was just a simple burst of events. This is a well-defined cascade, and this is a well-defined cascade. That's why these threw warnings. This one did not, because the algorithm can tell the difference. And so based on those, we threw the warning and stopped and said we believe the pin is slipped, even though we have not yet caused a laceration of the skin. We then went in and dissected at the location of pin 3, which slipped around 130 to 150 pounds. And what we saw was a very clear mark where the pin was originally seated, and then about a 3 millimeter slippage. So this demonstrates we had no false positives, And when we did throw a red light, it was indicative that the pin had come in unseated. It was slipping. Had we continued, that displacement can get to the point where the pin completely comes out of the skin or starts to tear the skin and cause a laceration. Okay, so we've been able to detect breakage and slippage. We also wanted to alert when fracture has just occurred. So let's say that on a patient, the surgical team installs the sensors. We always see some events coming from the pins becoming slowly embedded into the skin. Those are typically associated with a with a decreasing event rate. But can we tell if there was actually a fracture? And we go back for inspiration to some experiments that we did on rocks again a few years ago, where we ran these beam experiments and we increased the load now to failure. We recorded the cumulative events, but we did something a little bit different. After the test was over, we actually kept on recording the events for a long time. We took the two halves, we isolated them on rubber mats, and we continued to record events. And here's what we found. We found that we get, as one might expect, so this is 4 different stages. This is initial loading. This color code is on time prior to the failure of the sample. And we can see that as we get close to failure of the sample, all this red stuff is events that are happening temporally very close in time, and you can see spatially very close in space to the macroscopic failure. Post-failure is that minute and a half it took us to get the sample taken off from the supports and set on a rubber mat. And then we let it sit for about a week. And during this time, we continue to observe events. And they're true events. They're not, I mean, we had the system set pretty sensitively. We could see also like people opening and closing the door of the lab. That has a completely different event rate or different waveform. You can't locate those because they don't have a walkout of timing to your sensors. So very, very clearly, some things like room noise are not events. We had some things that were very clearly indicative of locatable events with the right waveform. And those continued for days. And if you look at the distribution of their magnitudes, it follows Gutenberg-Richter law in magnitude frequency distribution. And interestingly, and here's what we're going to use, the cumulative events after breakage follow this logarithmic growth, which indicates that the event rate is decaying hyperbolically. That's called the Omori-Utsu law, and it's well known in seismology as the aftershock decay law for earthquakes. And we actually see this exactly happens on skulls. Here's another case where right after we loaded to 40 pounds, we suspected that we had created a rapid fracture, or sorry, right after the load to 60 pounds. We suspected on the load from 40 to 60 pounds that the skull had fractured. And if you look from here, from 3 to 5, you can see this Omori-Utsu law aftershock sequence of events that takes place. This is the skull continuing to crackle after that initial break. Then we see a little bit later, there's a major shock, so a secondary breakage event here at 5 with another burst, and then decay according to Omori-Utsu law. So that's a distinctive pattern that again can be detected that says we suspect that the skull was broken during that pinning exercise. Okay, so now to conclude. So delayed breakage of these rock beams is preceded by systematic divergence of AE that can be used to predict the time to failure. An accurate time to failure can be had for the last 30 to 50% of a beam's lifetime. The skull emits a cascade of AE energy, both in the lead up under delayed conditions and associated with pin slippage, and can be used to give warning greater than 30 seconds in order to prevent patient injury. As a final step, I'd like to acknowledge support from R.K. Mellon Faculty Fellowship, and from a bunch of people who have been very instrumental in putting this together. I have a few other things, but I think that I could show, but I think for the sake of time, we might wrap up there since we're nearing the top of the hour and open it up for questions.
All right, all right, all right. So thank you, Andy, for fantastic presentation. So I think we have at least one question just pop up by Nicholas Espinoza. Um, so the question is, did you try three-point bending with fluid-saturated rock or bone to verify any fluid effects on subcritical fracture propagation?
Yeah, it's an interesting question. So we did, and what was really interesting to us in Granite is we actually, and we've published a paper on a few years ago. We thought people throw around words like electrolytic weakening, that would make one hypothesize that water saturation would lower that barrier to subcritical crack growth. And so you should have some water weakening, even of granite, because it lowers the barrier, the energy barrier to breaking a SiO bond. That's the hypothesis. We've seen it in the literature. We didn't see that at all in granite. We did see water leading to a lower time to failure. So it actually did impact. So water clearly does impact the breakage relative to a dry sample, but it actually impacts in exactly the same way as a hydrocarbon of the same viscosity. So in the crystalline rock, we believe actually it's probably more of a lubrication of grain boundaries than it is actually impacting the chemistry of SiO bond breakage. So that's in the three-point bending, that's what we've done as far as saturating with different types of fluids and looking at the effect.
All right, so we have next question from Seraphim Grubas. So how do you identify the correct cascade of the scalp failure among all?
Oh, how do you identify? So really, we have not seen clear cascades other than what has led to actual failure. So that distinctive cascade, when you plot the inverse AE energy rate, really only occurs when we've seen slippage or when we've seen demonstrable breakage. I can see that if you look at a first glance at our data, it might look different than that. Like you see the inverse energy rate going to zero, but it does it like instantaneously. That's when you turn on a drill, right? Or you touch the sample, you get a burst of events, but not with a progressive cascade. That cascade seems to be very robustly indicative. And it's actually really helpful in a surgical setting because there's lots of things that put your AE energy rate like shoot off to a really high value, like somebody starts drilling. But that does not produce that quasi-linear cascade to failure. So that's really probably the clearest way to pick it out. You can also do waveform filters, other types of things that trigger the system. Like for example, a drill has a very distinctive peak in its frequency spectrum at 30,000 hertz because that's how fast the tool on the drill bangs up against the skull bone when a surgeon is, doing a craniotomy.
All right, so we have the next question from Alan Katendi. So the question is, how does the rate-dependent failure model account for material heterogeneity and anisotropy when predicting time to failure in both rock and bone, given their different microstructural characteristics?
Yeah, I mean, so it's a good question. I don't know if continuum assumption per se is required for that model. You could see cascades in kind of finite sized lattice networks or members of a structure that has a cascade of failures, going through a kind of non-continuum structure or mesostructure. So I don't know if you need continuum assumption. Um, Heterogeneity is always going to make it hard to um, be predictive from one sample to the next, right? So, but I think in the case of you know, in some sense, it is a way of dealing with heterogeneity and variability. This is just philosophically why we went in for the skull case. Why do we do this and just monitor rather than a detailed CT scan and learn how to quickly feed it into an FEM model and then run an FEM model and come up with a peak pinning? It's because even if you have detailed structure in a CT scan, you have so much variability from one patient to the next of how well calcified the bone is that we decided we're going to handle the patient to patient heterogeneity better by just having a common feature of hopefully all or most bones when they fail that we can detect rather than trying to do something ab initio.
All right, so we have next question from Sean Maxwell. So he's wondering if there is any connection between rate-dependent failure model and rate state friction model used in seismology.
So, okay, there could be. Let me, okay. You've teased it out of me, Sean. I won't take time on this, but it's actually super difficult in the literature to kind of ascertain what makes this catastrophic model work. But here's my attempt. I think that what you need, these are the two ingredients. I think you need a rate of response that's a power law of some driver, and a driver that is in turn a power law of the accumulated response. That is the fundamental feedback loop from my perspective. So Ian Main pointed out that you could get to the same form. So this is this, if you put these two things together, you get Voigt's model. And you can see that alpha is going to be close to 2 for a lot of these because of how large the subcritical crack growth exponent is or the rate-dependent material exponent is. I think rate and state friction, exactly the same thing. You have something where you have a response that is a power law of a driver and a driver that is a power law of the accumulated response. I think it probably would lead to this type of model if you plug it in with that type of format. But this is like, okay, I didn't put it in. I was a little scared. I haven't published it yet. And it's just like my own musings on what I think is the fundamental ingredients that are required to generate Voigt's model. Main pointed out that this can lead to Voigt's model, and you can kind of get yourself inspired off from it and say, well, there's a lot of things that could lead to Voigt's model.
All right, so we have another question. I mean, it says user's iPad, but I think it's Anthony Pierce. Has this early warning system actually been used in real surgeries yet?
That's what we're working on right now. So there's a NSF R21 or NIH deadline this month. So we are trying to get this into the OR. If we're successful at getting funding, we would hopefully have it see its first 100 patients starting around next summer. It would be non-FDA approved, which means we would be able to observe but not impact the proceedings. So we could observe only and collect data that would lead, hopefully, in the future to FDA approval.
That's good. Okay, so we have one more question just showed up in the chat from Ella Maria Llanos. What are your thoughts on how does the energy release and fracture propagation in cascade failure of skulls compare quantitatively to that in layered or joint rock masses under similar stress conditions? So I guess
Yeah, I mean, I think, yeah, so the layered and jointed rock masses is an interesting question. Yeah, I mean, I think that they probably, so the previous slide that I showed briefly, what I believe it shows is that you can have lots of things that follow that format of a basic feedback law where you have a rate of something is a power law of a driver. Driver is in turn power law of the accumulated response. I think that can take place for probably even in society. Like catastrophic collapse of a societal system, probably you could model. So my guess is that both systems would follow this cascade, but it might be due to different underlying mechanical principles. But the fact that so many things seem to follow that power law relationship and that feedback, that they kind of at the end of the day show this Voigt type cascade. And in fact, Voigt in his original paper in 1989 did a lot of musing because he was very puzzled as to why it's so ubiquitous. But I think the answer to why it's so ubiquitous is that there are a lot of things that when we get interested in things that fail catastrophically, and things fail catastrophically because of a certain feedback loop. Um, and there's a lot of things that have these kind of power laws for whatever reason.
Great. So I think we have no more questions in the chat. Well, actually, I have one practical question for you. I mean, first of all, I mean, this device looked like a little bit of a torture device, the one that you show on the picture. But apart from that, you see you have two pins on the right and one pin on the left, which makes higher load on the left. And so the question is, my question is about the design. So what's the reason behind having 1 plus 2 pins? Why don't people using 2 plus 2 or 3 plus 3? Because the more pins you use, the less load you have per pin, and probably so less load you can apply, and so you have less chances of having punctures through the skull.
Yeah, I mean, I think so. The device is fairly old and robust, and allows the surgeon, surgeons become comfortable with it, and they can kind of move on with their lives. So I think that's why there's a legacy factor here. Um, I would say, like, let's say we came up with something to spread it out among many pins. At the end of the day, a patient is going to come out of the surgery with more punctures in their skull. The other thing is, if you think about like designing like a milking stool for, like the classic milking stool to sit on when you're milking a cow, you design it with 3 legs because those 3 legs will sit in contact with minimal wobbling,
Hmm.
right? If you have a 4-legged table, and one leg is a little bit off, you can get the wobbling. In this case, wobbling is not good because it can lead to pin slippage. So I think it's kind of a 3-legged stool idea, that you have kind of a minimum number of contact points that try to give you the most even distribution, even though one is double the other two. And in adults, the main problem is on the one pin side, things can start to slip or the skull can creep, and they do get slippage fairly, too commonly. That slippage would probably be exacerbated by a system with many pins.
Makes sense. Thank you. We have a couple more. Let's make them short. Um, so the next one is there any way to define micro cracks properly occurring before and after failure of rock sample? And to what extent do they affect acoustic emission event measurements?
The micro crack what?
Uh, is there any way to define micro cracks properly occurring before or after failure of rock sample?
Yeah, I mean, all we do is measure an event. The event has a certain waveform, um, that we recognize as being distinct from, hitting with the sample with a tool or room noise, and it walks out from among the sensors when we have multi-sensor tests. That's really all we can say. The whole microcrack part is essentially a big, um, it's a big unifying conjecture that we all use to explain why events cascade in a certain way and why rate dependent materials fail in the same way. In a certain way. There's a lot of things that are unified by this idea of microcrack coalescence, but often hard to see except in like experiments where you make not microcracks, but much larger cracks that you can see coalesce.
Mhm. Great. Then the last question, and then I know we're exactly an hour, a couple of minutes late. So last question, I think it's quite an interesting one. So in your experiments, um, how was the acoustic emission energy rate quantitatively correlated with mechanical stress or deformation prior to failure?
So we were holding, so except in the pinning case where our rough and ready system wasn't holding stress very steadily. In the other cases, we were holding a constant load. And so we were measuring the acoustic emission energy in the way that I explained by taking a cumulative of the amplitude times duration. Correlated mechanical just temporally. I don't know. Maybe I'm not fully understanding the question.
I guess the question is how acoustic emission energy is related to mechanical deformation. So, elastic deformation of the skull.
Oh, I see. I see. Yeah, we don't have good measure of the elastic deformation of the skull. It's very, very difficult to get a measurement um, in where we're working. So it's a really good question. Something that one would kind of do ex situ with some bone in a loading apparatus. We haven't been able to do that yet, but yeah, where you would basically measure like do a full creep test, right? And looking at deformation going through stage 1, 2, 3 of creep and looking at how the acoustic emission tracks it. That'd be really interesting to do, but we haven't done it yet.
All right. I think we are finished with all the questions. Fantastic presentation, Andy. Thank you everyone for attending. So that's great.